Okay, so we're going to start on amines and amides today. An amine is an NH2 group, and it's in some ways similar to oxygen. So what I want to talk about first is the structural differences between nitrogen and oxygen. So nitrogen, we do a Lewis structure for nitrogen. It looks like this. Say for ammonia. And water. So oxygen has two pairs of unbonded electrons. Nitrogen has one. Fluorine has three. Now, because they have so many unbonded electrons, they tend to be much closer to the nucleus. So because of that, they're much more influential. So hydrogen bonding occurs. NOF. That's where the hydrogen bonding comes in. And that's where the familiarity between oxygen and nitrogen come into play. Now, the thing about fluorine, because it just has one singleton, it's kind of simple the way it bonds. But those other two, particularly oxygen, can have some interesting coordinate covalent bonds that bonds with the non-bonding electrons. So if we look at nitrogen, if we look at NH3 and an acidic proton, that acidic proton has no electrons. So it wants to bond. So what it does is it bonds with electron pairs. And that's called a coordinate covalent bond. Same thing happens with oxygen. That's where we come up with the hydronium ion, H3O. That proton forms a coordinate covalent bond with one of the lone pairs on the oxygen. However, it doesn't do it twice, it only does it once. And that's much more, bless you, twice. And that's much more stable than a plain old H. Much more stable. So that's why it happens. Now, another thing about both oxygen and nitrogen, because of the non-bonding pairs, until the allergies are out, my eyes are starting to itch. And you're sneezing. They tend to be very electronegative. Very electronegative. And because they're very electronegative, they have a very high intermolecular force component to it. So we're going to see in a minute here that nitrogen forms a partial negative charge. So, like alcohols, which has primary, secondary, tertiary, same with amines. We have primary, tertiary, primary, secondary, tertiary. And it has to do with the, just like with alcohols, how many hydrogens are there? 2 hydrogens with a alcohol is primary, 2 hydrogens with an amine is primary. And then none. It's the same thing. And you need to be able to identify, is this a primary, secondary, etc. Like ethers, frequently amines are named in a common way. So for example, what's attached to the nitrogen? Methylamine, dimethylamine, or if it's different, ethyl methylamine. That's the common way of naming these, not the IUPAC way though. IUPAC naming is where the amine is a functional group off of the main backbone. So we go back to the 3 parts again. We've got backbone, functional group, and then branching. So backbone, functional group, branch. Backbone, functional group, branching. And the common names are used a lot. Now, one thing about if you have an amino group that's a branch, you can also have substitutions off the nitrogen. And that's what complicates the IUPAC naming. So let's name let's name that. Okay, so backbone is 1, 2, 3, 4. Then alcohol. So that's 1, 2, 3, 3 amino, 1 butanol. However, what if instead of hydrogens on the nitrogen, we had methyls on there or ethyls? So let's do the same thing. That. How do we name that? The way you name that is, okay, it's got 4 carbons, so it's going to be butanol, primary alcohol. Okay, the branch, though, is, if you look at the way they name stuff here, notice uppercase, italicized N. So N-methyl. Butanol. Okay, so the big N is what's hanging off of the nitrogen. Now, what if you had So it's five carbons long. Like that. How would you name that? Okay, it's 5 carbons, primary alcohol. Okay, so we have 2 methyl groups coming off the nitrogen. So you would go N dimethyl. One pentanol. And that could be N-ethyl, or excuse me, N-ethyl methyl 1 pentanol. Say the other was if this was a ethyl group over there. We name it N-ethyl methyl 1 pentanol. Now, when we get to amides, which are like esters, we're using the same concept in naming. Now, when we talk about aromatic amines, it's based on the benzene ring with an amino group on it, so it's called aniline. So that's the base unit. So if we look at this one over here, we've got a methyl group hanging off the nitrogen, so that's going to require a capital N in front here. And then we have another branch, 1 over. So bless you. Again. Okay. So again, the capital N is for what's coming off of the nitrogen. And if we had 2 methyls, then it would be N dimethyl aniline. Okay, does that make sense? Now, because the nitrogen is electronegative, you're going to have hydrogen bonding. So the nitrogen is partially negative. One of the hydrogens is going to be partially positive. And since this is partially negative, partially positive, then you get the hydrogen bonding that way. Or let's see, let's do this differently here. Also, amines dissolve in water as well, for the same reason, hydrogen bonding. Okay, so if you look at the melting points. The bigger the molecule, the higher the melting point. But the boiling points don't necessarily follow that trend. So you're looking at, so this would be a primary, primary, secondary, secondary, tertiary, tertiary. So those jump around quite a bit. Now, the more hydrogens you have around the nitrogen, the more hydrogen bonding you can get. This has, not only it has none, it has steric hindrance. In other words, those R groups around the nitrogen restrict the water coming in to be able to bond with that partially negative nitrogen. Or over here with hydrogens, with the primary, there's a lot more room to get in there. So this has much higher that's supposed to be a C. So the third degree, or tertiary amine, has low hydrogen bonding because there's not hydrogens present. And secondly, you have steric hindrance going on. Amines, like sulfur compounds, usually are stinky. In fact, when you have rotting flesh, these are the two amines that contribute to that awful odor. And they're aptly named cadaverine, putrescine. Now, amines can act like bases. So if they act like a base, that means they want to attract protons or hydrogen pluses. Okay. So the bases will grab one of the H's off the water, and that yields a hydroxide ion. So when you take ammonia for cleaning grease, the ammonia is not what cleans the grease. It's when it's mixed with water, it forms an hydroxide ion, and that's what saponifies the triglyceride grease. That's why ammonia works for greasy stuff. So when you buy Windex, there's two kinds of Windex, with ammonia, no ammonia. So when you want Windex for your windows that has no grease on it, unless it's by your stove, you want to use the ammonia or the ammonia-free Windex. If it's around your stove or to clean your stove, you want to use the Windex with ammonia in it, or just straight ammonia. It's cheaper to buy straight ammonia. Now, when one of these one of these H's from the water goes over to the nitrogen, you form an NH3 plus ion, and that's called ammonium. Now, if you remember from 305, possibly, one of the cations, common cations, is NH4 plus. And how you derive that is from throwing ammonia into water, and you end up with NH4 plus. Okay, so whenever we have amines in pH less than 7, we end up becoming an ion, an ammonium salt or an amine salt. So for example, look at methylamine down here. We add an acid, hydrochloric acid, we end up with methyl ammonium chloride, okay? So it's amine versus ammonium. So if we have a weak acid, and an acidic acid environment, there'd be no reaction. So in a basic or alkaline environment, a weak acid, you'll end up with the acid salt. So an amine in an acidic environment, you end up with the ammonium salt. Amine in an alkaline environment, no reaction. So the acids and amine bases are the opposite and opposite ends of the pH spectrum. Now, you saw this on the last test. You're going to see it again on the next test. Okay, so here we have an amine, acidic environment. We end up with the ammonium salt. So when we name an ammonium cation or an ammonium ion, we're going to be using the ammonium and the salt associated with that. And then you name the branches off the nitrogen. And there's going to be, could be 2, 3, whatever. So in this case, we have an ethyl group, 2 methyls. So it's going to be ethyl dimethyl ammonium bromide. In this case, we had 3 acetates, excuse me, 3 ethyl groups. So it's going to be triethyl ammonium acetate. And this is the acetate anion. Now, Okay. The ammonium ion is ionic. That's the highest form of intermolecular force. So if we look at, again, the intermolecular force table, we go ionic, H bonding, dipole, dipole, LDF. So the ionic is by far the strongest. Then come hydrogen bonding, then dipole, dipole. And some of you, your permanent dipole instead of dipole, dipole. And it depends on what book you're reading. And I abbreviate everything because it's really long to so frequently when manufacturers make drugs and it has nitrogen in it, they will take the nitrogen and make it into an ammonium ion, like morphine versus morphine sulfate. And a lot of drugs have nitrogen in it. A lot of biological molecules have nitrogen in it. For example, your DNA, your RNA, they all have nitrogens in them. Now, this hydrogen plus there can be taken away by just adding something that wants that hydrogen plus, like a strong base. If you throw an acid in it, it's going to stay this way. If you throw a base in, it's going to stay that way. So you can manipulate the ionic character of that nitrogen by changing the pH. Just like the way I worded the on the test, the way I worded the acid. Is this, describe the ionic state of this. So we have primary, secondary, tertiary, and we also have quaternary. You can have 4 things attached to the nitrogen because of that lone non-bonding pair. And that becomes an ion. The way you structure that is with square brackets and the charge is out there. Just like when you're doing Lewis structures, do the same thing. Do the Lewis structure, square brackets, charge. Now, from the biochemistry from lipids, we talked about choline. Choline is a 2-carbon backbone that's both an alcohol and an quaternary amine. So that's the quaternary amine there. That's where the plus charge located. Now, I don't know if you've heard of acetylcholine. Who's taking biology in here? Anyone? Okay, well, you're going to be studying a nerve synapses, and what triggers a nerve is called a neurotransmitter. That's what goes across the opening. It's called a synapse between 2 nerves. Those are called neurotransmitters. Acetylcholine is one of them. Oh, excuse me. Acetylcholine is one of them. Now, there's a pesticide called acetylcholine esterase inhibitor. So what happens is, the way this works is acetylcholine travels across the nerve synapse and it sticks there. And then the nerve can't function until that's released. And that's what the enzyme cholinesterase does. it pulls that acetylcholine out of there. If you inhibit that enzyme, then that enzyme can't pull acetylcholine out of there, and the nerve is dead, can't function anymore. So early pesticides, organophosphate pesticides, were called acetylcholinesterase inhibitors. And they also work pretty well on humans as well. When I had my ranch in Winters, we had walnuts, and they would frequently, we had about 10 acres of almonds and 110 acres of walnuts. And on the 10 acres of almonds, we had to use bees to pollinate the almond flowers. And we also had an issue with navel orangeworm. So we had this dichotomy. Do we kill the navel orangeworm with pesticides, but we can't harm the bees because then the bees won't fertilize the flowers? A real problem. That's why organic stuff costs more, because your yields are down. And so we ended up spraying anyway, and we killed some of the bees. It was a matter of we had to protect these almond trees. So it was a tough choice. So the stronger bees survived fine. The weak ones, the old ones, and the weak ones didn't. Again, we turn this drug into an ionic form, so it's the motility in the blood is higher. Blood, as you know, is mostly water, very polar. So if you want something to move in blood, it's got to be polar. Otherwise, it'll just sit there. Okay. Now, amines can react with acids, just like alcohols can react with acids. For the same reason alcohols react with acids, the nitrogen looks enough like an alcohol to do the same reaction. The mechanism is exactly the same. So instead of a C double bonded O, we have a C double bonded N. It's called an amide. And this is where proteins are put together with an amino acid, because on one end of the amino acid is an amino group, hence the name, and the other end is an acidic group. So they can form long chains by forming on the acidic end of the amino acid, on the amino end, they come together and form an amide or a peptide bond. Probably heard that. So like we did with esters, say we had that, where this part is the alcohol. Over here was the acid part. So if we have an amide, this would come from the amine and acid. So esters are in two parts, amides are in two parts. And the way you form these things is the same reactions as the three ways you form an ester. Okay, now, there were three ways to form an ester: with the acid chloride, and the acid amine. Okay, so let's say so this would be dipropyl anhydride plus, and this would be the acid part of the ester. And then we throw in some like ethanol, the alcohol, and we would then get that. So that's ethyl butanoate. Okay, so if we do the same thing, use the same anhydride, with the amine, we're going to end up with an amide. So this is the ester. So this would be must be N in there. Butamide. Now notice there's no N there because there are only hydrogens here. I didn't have any alkaline groups there, like methyl, ethyl, or whatever. Now you can do the same thing. You do the same thing with using the same anhydride. Oh, excuse me. Let me back up here. We can make the same amide. Instead of using the anhydride, we can use the acid chloride. So that would be plus NH3 gives us that. However, if we started with the acid, we would not get a reaction. We would actually get one, but it would be extremely low yield, almost to the point of being no reaction. You do get a reaction though. Important to understand that. It's just the yield is so crazily low. Okay, so we make an amide. There's only two ways to make an amide. There's a third way, fails. So with an ester, we have three full ways: acid, anhydride, acid chloride, amide, no acid, acid chloride, and then hydride works fine. Okay, so with the acid chloride plus the the amine gives us an amide. When we use the anhydride, it also kicks off the other half of the, remember, an anhydride is two esters together. When we use the acid part of the anhydride, it kicks off the acid part of the other ester. You end up with an acid, like we made our aspirin. Salicylic acid. So what we did is we connected up the OH part of salicylic acid, which form the alcohol, plus the anhydride. Because we used the anhydride, it kicked off acetic acid as a byproduct. That's why we had to purify it to get rid of that acid left over. Okay, so naming amides. Okay, so like we name esters, so let's name it ester here. Okay, so it's 2-carbon alcohol, 3-carbon, or excuse me, 4-carbon acid. So we're going to end up with ethyl, butanoate. If we have an amide version of this, so now we have an alkyl group off of that nitrogen, not just hydrogens. So we have to specify with a capital N what that branch off the nitrogen is. So like this comes from the alcohol part, acid part. So we name an amide, we do the same thing. We have an alcohol part, we have a acid part. So the acid part is 1, 2, 3, 4. But the amine, though, has got a branch off of the nitrogen. So we have to go N, just like we specified the alcohol part in the beginning. Oh, it's not alcohol, it's the amine. So like we did the alcohol at first, we're going to do the amine first. Okay, it's a nitrogen branch. So we have to specify N-ethyl. Now, so N-ethyl butamide. So that's what they're doing over here. So when we name this, this has 2 branches off the nitrogen. So we have to go NN dimethyl benzamide. Okay, so an amine, basically just amine by itself with no acid products around, will in water forms the ammonium ion plus OH negative. That's why they call it a base. If you throw the anhydride in and an acid, we'll end up with an amide. Or if we throw it in the acid chloride, we'll form an amide. Okay, so 2 ways, not 3 ways to make an amide. Amides are very important in biological systems. All enzymes, because enzymes are made of proteins, require an amide. That's called a peptide bond. So they're very important. So, all right. A lot of people didn't get their tests back. Okay. Now I said we wouldn't cover artificial polymers, but a lot of plastics are made with amide bonds. You all heard of nylon. Nylon is made with amide bonds. Including biological polymers made out of that are made with amines, like proteins. Silk and wool, very natural fibers, are made of amines. Okay, so this is the gap I was telling you about between two nerves. Okay, so this is it labeled? Yeah, this is the synapse gap. And that's how one nerve talks to another nerve. To do that, it does it via something called neurotransmitters. And this is indicated with these little triangles here. So they come over and they have receptors there where the neurotransmitter fits into those receptors. Once it fits into the receptor, the nerve is turned on. So it bursts electrical energy. And then, unless that site is removed, so if you have a neurotransmitter here, and that is not enzymatically removed, that neuron cannot function anymore until that's removed. So that's why if the neurotransmitters acetylcholine, you need an enzyme called acetylcholine esterase, which pulls that out. And then the neuron can function. This is the way many nerve poisons work, by screwing up your nerves, the synapse and the neurotransmitters. And there's quite a few neurotransmitters, and all of them have receptors on the other end of the gap. And each one has to be pulled out and recycled. There are antidepressants called SSRIs that actually work like this. And what they do is they inhibit the enzyme from pulling it out. So it slows the reaction of that neuron down. And they're called SSRIs. There's a bunch of those out there. You've all heard of dopamine, serotonin. Here's acetylcholine down at the bottom right. And these are all neurotransmitters. And you need an associated enzyme that works to pull that out of the other side of the synapse gap receptor site. And there's a lot of, now, I don't want you to know these. I want you to know that they exist. I don't want you, for example, memorize dopamine. I want you to memorize choline and acetylcholine. Those are the only two. But a lot of these others, dopamine, you've probably heard of dopamine. There's a lot of things that increase dopamine, which is a sense of well-being. And now this is a good reason why you should have a healthy diet. Many neurotransmitters are synthesized from amino acids. For example, tryptophan, it's an amino acid. So we can take tryptophan and make it into serotonin. So if you don't have a diet with tryptophan in it, it's hard to make serotonin. That means you have certain nerves that don't function very well because there's a lack of serotonin. So there's a lot of good reasons to have a good, healthy diet. Adrenaline is another one. Notice how many biological compounds have nitrogen in it. You know, adrenaline, amphetamine, epinephrine. I mean, it goes on and on. It's amazing. And of course, there are other nitrogen compounds You all have heard of speed or amphetamine. This is what it looks like. One of them. There are many versions of this. Notice again, it's an amine. It's a secondary amine right there. Okay, alkaloids. They also contain these nitrogen compounds. A good example is nicotine. There's good old caffeine. Look on your lab packet, and the cover is a picture of caffeine. So this has no hydrogens attached to it. So that's a tertiary amine. Tertiary amine. Tertiary amine. Tertiary amine. All these are tertiary amines. There's a number of biological heterocyclics that look like this. Uh, 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 penicillin has got a structure similar to that. It's kind of like a dual ring structure. It's very interesting. Good old opium. Look at the difference between codeine and opium. Okay, so this is opium on the top. Excuse me, morphine on the top, codeine on the bottom, and then there's morphine comes from opium. So you can take and modify morphine into codeine. And let me show you another modification you can do from morphine. So we've got and then we have, okay, there's that. And then let me, okay, so that's morphine. So this is how you make heroin. You take those two OHs and converted the H to a methyl group. This is now heroin. That's how you make heroin. Start with morphine from opium, turn the OHs into methoxy groups, you have heroin. And that's a very easy reaction. The problem is, if you do it in a poor environment, you get something called tar heroin, which has a whole bunch of impurities in it. And it gets you high, but all the impurities really do a job on your body. And that's what street heroin looks like. Because it's easy to make, unfortunately. Now you can go home and think that you learned how to make heroin in here. Yep, there's heroin. Okay. Okay, we already talked about naming. Amines are not as high of intermolecular forces as the amine. It's because the amines tied up more. So they're still can do hydrogen bonding and everything, but not as well as a bare amine. Now this time, instead of being attached to the the nitrogen is attached to the oxygen on the carbonyl group from the acid part. Now, amines are basic. Amides are not. They're neutral. Unless you take them apart. We hydrolyze them, then they become separate amines in the acid. So if this is a protein, we have an amide acid attached together to make an amide. In our stomach, we have something called an enzyme called a protease that breaks up an amide bond. And that's called protein digestion. So the hydrolysis of an amide bond, taking it apart, is biologically really important. Oops. So if the amide is in an acidic environment, you'll end up with the amine salt and the acid. If it's in a alkaline environment, you end up with the acid salt and the non-ionic amine. Okay, so because in your stomach, is that an acidic environment or an alkaline environment? What do you guys think? Stomach. Who in here has thrown up? Anyone? Okay. And that's not a pleasant experience because you're tasting something very sour. Guess what that sourness is? Stomach acid. So your stomach is a very acidic environment, pH of 2. So this is the environment in your stomach. In fact, it's hydrochloric acid. What happens then, it breaks up the amino acids from another. So what leaves your stomach is a whole series of amino acids that were created to make the protein that you ate. Okay. So acid environment, we create the acid part, and we create the amine part. So that's the amine acid amine. In that hydrochloric acid environment, we create the ionic form of the amine, ammonium chloride. When we're in a basic environment, we still create the amine from which we started with, and we create the acid salt. So again, you guys need to know this. And you don't have to worry about these, but these are kind of interesting. Notice again, the amount of oxygen and nitrogens and biological compounds. They're ubiquitous. They're all over the place. This is the common structure for penicillin. All the forms of penicillin have that structure there in it. Oh, there are no more slides. Okay, so on this unit, don't worry about the large biological drugs and that stuff, okay? You need to know there are amides in there and ketones, all that junk. But as far as knowing those structures, don't spend time memorizing the structures. You do have to understand how to put an amide together and what happens when an amide comes apart in different pHs. You also need to know the series of amine reactions as well. Yeah. You found them, right? Oh, I have two versions, I guess. One of them, I took out the bones. So, yeah, so you don't have to worry about it anyway. But the slides are available, though. Right, okay, good. Because I bet you it says short form after it. Oh, okay. All right, well, that's it for today. I will get this video created, and then I'll see you upstairs.